Here are two different examples of accelerating systems that have an object hanging from a string, and at this point in my students' year, typically I hand these out at the same time as part of, a review sort of sheet, but I call these are tough problems, especially when they come together. And they're tough because it can be pretty hard to tell, or it can be confusing to say what's supposed to get broken into components and what isn't. All right, and there's a semi-simple answer to that question, and it's if you are a person that's going to be required to do some problems about forces and dynamics, it's a question you need to be able to answer. All right, and the question is this. I'm going to type instead of writing. The question is, drum roll, the question is, what direction does the object slash system accelerate? All right, and the answer to that question is, then that's one of your coordinate axes. All right, you have to be able to identify that, the answer to the first, and then that tells you, okay, those are the axes I use. Anything on axis I leave alone. Anything off axis I break into components. All right, so I'm not going to even provide the text of this question, but the train car thing on the left, we have a ball from a string attached to the roof of the train car, and the train car accelerates to the right, and that means that the ball accelerates to the right. Now, some people, kids in my class will say, all right, well, if the train car accelerates to the right, then that means the ball accelerates to the left. That is just plain old not true. All right? This ball is attached to the train car. And as the train car accelerates, so does the ball. All right, so the answer in our train car example here is that every part of this system accelerates that way. And thus, our axes are that one and this one. As opposed to, in this question about a pretty sick minivan here with a ball attached to the roof, and that, I don't know what this U is supposed to be. I think that's supposed to be a theta, probably. So we'll forget about that U. But here's a ball attached to the roof of a car, and the car, as phrased in the question, is accelerating down the hill. All right, well, the ball is attached to the car, and things that are attached to each other accelerate at the same rate. So that means for this example, the axes you use are this and that. Now, axes that we use are always perpendicular to each other. They have to be. That way we can say there are forces in one dimension that have nothing to do with acceleration in a perpendicular dimension. All right? And I get that this seems like a simple question, and identifying the answer to that question can be challenging, I suppose, but you have to be able to ask it. You have to be able to think about it and then make the right choice about, well, the answer to the question and therefore the axes that you use. So, with that in mind, here is a free body diagram for this hanging ball, mg and tension. That's it. Nothing is pushing the ball to the right. Sorry, left. Nothing is pushing the ball to the left. Well, how come that angle's there? Well, because, right, using our red axes, there is a component of t that points that direction. There is a component of t that points in that direction. Here's our angle, right? It's measured from the vertical. Okay, from the vertical. There's no applied force. There's nothing pushing on that ball. Right? The string pulls at an angle because the string accelerates the object to the right via that component of t to the right. So our net force statement for this is that Tx equals ma. That's it. Now, a bit non-standard because the angle's here measured from the vertical, so Tx is opposite that angle, so this goes as t sine theta in this example. The other net force statement you can write is that Ty equals mg. Well, excuse me, really Ty minus mg equals may, but in this dimension the acceleration is 0, so those two forces are equal in magnitude. Now, this is T cos theta equals mg. My approach here is to use this equation to solve for t. Insert that solution for t into there. So you'll get t is mg divided by cos theta. So here we'll have mg divided by cos theta times sine theta equals ma. Your m's will go away, I'll just do it. Right? So from here, we get t is mg divided by cos theta. That goes into our expression where I drew that arrow. So this turns into mg over cos theta, that's t, this is t, times sine theta equals ma. M's are gone, and we get g sine theta divided by cosine theta is tangent theta. There's your answer. If we're looking for an answer. I mean, if we're looking for an acceleration, which we probably are in this one. They give you the mass, right? But it's unnecessary. Any and every object, when the train accelerates at that rate, will swing out to the same angle. Okay? Okay. As opposed to, let me take this stuff. Oh boy. Yeah. As opposed to in this question, when the object as part of this system with the car accelerates down the hill, okay, well here's a free body diagram for the object. Well, mg points down and t points this way, right? Here is the string. Sorry, here is the string that pulls that way. So it's a very similar free body diagram, except now this is part of, these are forces acting on a system that's accelerating down this incline, so our axes are like I drew here. Those are our axes. And so that means now mg is the off-axis force. So what we do is break mg into components. There's mg parallel. There's mg perpendicular. And this angle from the vertical to the tension is the same as this angle here. So the two net force statements we can write from this are, well, mg parallel equals ma. This is going to be mg sine theta equals ma. And if you want, again, I don't know what this question asks, I don't care. The other net force, so this is net force in the parallel direction. Net force in the perpendicular direction says T minus mg perp equals 0, so T equals mg perp. Or T is mg cos theta. All right, I know that that perpendicular involves cosine theta because it's adjacent to the angle, right? I know that mg parallel involves sine of theta because here's mg parallel down here, opposite the angle. I'm invoking SOHCAHTOA when I talk about adjacent and opposite, the definitions of sine and cosine. All right, so again, I don't know what this question is asking for, to tell you the truth, and I don't really care. Or maybe it's I don't know. I don't know. Doesn't matter. All right, whatever you need to know, you can get the answer from this expression and this expression. Okay? The more important point is this. How do you know which axes to use? How do you know which force to break into components and which one to leave alone? All right? The answer is you must be able to ask yourself this question. And asking the question is not the hard part. The hard part is knowing the answer and being able to justify the answer. And what you have to be able to recognize in questions like these that are a little bit wacky is that systems of objects that are connected physically by rigid, non-stretchy strings or other things accelerate at the same rate. So if train car accelerates right, ball is accelerating right. If minivan accelerates down the incline, then this ball accelerates down the incline. Okay? Hope that helps. Adios.